In this video, we demonstrate how we solve an intractable helicopter scheduling problem for the oil and gas industry. The goal is to find a routing schedule that meets all daily transportation requests while minimizing the overall flight time and therefore distance and cost. Here, we'll show how MEM computing scales to solve this problem more efficiently and accurately than best-in-class solutions. Once logged in, we see the user interface where we can set up, solve, and review the solution of this scheduling problem. This demonstration shows the scheduling of a fleet of helicopters that are used to transport passengers from a heliport on land to, from, and between oil rigs in the Gulf of Mexico. So first, we'll show you the pad configuration that identifies which helicopters are supported by each landing pad. Note that this could just as easily be airplanes and airports all around the world, as some planes may need longer runways. For this problem, we consider two different types of helicopters. In this demonstration, the location of the heliport and oil rigs is identified by this distance matrix. For airplanes, this might be a list of airports and the latitude and longitude. We can also import data from a map. Lastly, we show the configuration of the fleet of helicopters. In this case, the client has 13 of each of the two helicopter models, the Bell 407 and Bell 412, for a total of 26 helicopters. When scheduling these helicopters, all helicopters may not be used and some helicopters can have multiple flights. Note that all of the associated data with each helicopter can be different. It also does not matter how many different types of helicopters or aircraft are used. We just need to know the available aircraft, their current location, and all of the pertinent constraints. For airplanes, the max weight of passengers, luggage, and max range will obviously be much larger. The actual value of these constraints does not affect the scale or complexity of the problem. Now, let's create a new scheduling job. We must simply upload today's manifest, although we can also integrate directly to and pull it from your data lake. In this case, we have 300 passengers that need to be scheduled. The manifest identifies where each passenger starts, where they need to go, their weight, and the weight of their luggage. The weights are required because the helicopters have maximum weight constraints for passengers and luggage that must be maintained. For this particular problem, the passengers are assigned flights and times. We also support the variation where the passengers must be at a specific location at a certain time. Now, all we have to do is run the problem. Here, we can see our solver working to find the optimal scheduling solution. Remember, it is searching for the shortest overall flight time for the fleet while satisfying every transportation request, which directly correlates to minimizing the cost. After it is finished running, we can view the results. We see that our solver ran 4 iterations taking about 2 minutes. The first iteration provided an optimized solution within 30 seconds. Seeing that there was some room for improvement, our solution iterated further, finding a better solution that more closely approached the optimum, returning a total flight time of 26 hours 52 minutes. While this seems easy for MEM computing, we benchmarked this problem with other commercial solvers. Because of the combinatorial nature of this problem, commercial solvers would take weeks, if not months, to find an optimized solution. If we review the daily manifest, we can see that each passenger has now been assigned to a helicopter. This data can be exported, where we can then email it or send directly to the client's data lake. Looking at the helicopter configuration, we can review the data of each flight. For this helicopter, we see the assigned list of passengers, their starting location, and final destination. The graph in the upper left-hand corner represents the path the helicopter will take, and it stops at the rigs along the way. Note this is not to scale. The graph beneath it represents the flight time of the helicopter along its route, with the red line representing the maximum flight time range. Of course, we stay beneath this range and can see that at stop 5, it has returned to the heliport. In the right-hand corner, we can see that as it leaves the heliport, it has 3 passengers on board. When it reaches rig R, it drops off those passengers, then travels to rig C to pick up 6 more passengers, the maximum number it can hold. It then flies to rig J to drop them off and returns back to the heliport. The final graph shows the weight on board the aircraft as it follows its scheduled flight. If we click on the arrow to the right, we see that this helicopter has 3 flights assigned to it. That was because, timing-wise, when it returns to the heliport, it is optimal to send that helicopter back out rather than assigning the next flight to another helicopter. Note that if we scroll down, we can see that this helicopter has no scheduled passengers, demonstrating how the optimization of the schedule does not require the use of every helicopter. We can look at these details for each flight in the schedule. Again, this information can be exported or integrated directly into the customer's solution. This scheduling solution reflects the loading and routing assignment of 300 passengers using up to 26 helicopters for travel to, from, and between offshore rigs that minimizes the total flight time. The case study we ran showed an annual cost savings of more than $20 million and dramatically reduced greenhouse gas emissions. Other solutions available today cannot scale to include all of the operational constraints and variables. Instead, these solutions use heuristics, which render approximate suboptimal solutions, which results in much higher operational costs. MemComputing's novel new technology provides an optimal solution in very little time, enabling our clients to achieve new levels of operational efficiencies and the ability to quickly reschedule flights should a disruption occur. For more information regarding our passenger scheduling solution, visit our website and read the full case study.